All right, you've gotten some experience of seeing, visualizing how electric fields are storing energy around charges. One way we do that are by these field lines. The tighter they are, the more field there is, and usually that means there's a larger charge at the center of those that are giving off those field lines. It's just a visualization tool. Does it really exist? It's questionable. I mean, we don't have any other proof than it's just a good tool for us to visualize these. We got some practice in a simulation to be able to look at some of those field lines, and then we did some calculations. Again, the electric field was the sort of influence that charge sets up around it, but it doesn't have a second charge to then interact. Once you know the electric field, if you put that second charge in, you're just basically doing this, saying, oh, I know what the force is between two charges. But if you take the electric field and supply that second charge, you actually do have this same formula. This is the force per coulomb that you would put, into a field, and down here it's just going to be the force because you know all the size of the charges. They look exactly the same. It's 9 billion times the two charges divided by the distance squared between those two charges. The closer you get, usually the higher the force. If they're at the same charge, it's going to be against. If they're the opposite charge, they're going to be towards each other. Finally, we get this potential to do work, and if you change the position of two charges to each other, it's going to take energy. That's a force, which you just calculated, times that distance. And so if you know the two distances you're talking about, you can calculate how much energy that takes. And those will have some interesting implications in the chemistry section next unit. But you could take 9 billion there times the two charges, and instead of dividing by distance squared, because force times distance is a work, so you're going to take one of those distances out, and that'll determine how the voltages have been calculated. So those are all the terms and all the calculations we do for static, stable electricity that gets charged around a balloon, or that gets charged on a rod, or that's being generated by pushing, they're scaring the electrons down a string on a kite like Thomas Jefferson or Benjamin Franklin did. But let's talk about then the moving electrons. When you put those into a channel and they want to do work, that's what we want. We want to put electrons through a radio so we can hear it, or through a blender so we can use that in the morning. So those are going to have some terms that we should talk about too, and it's not that they're the same terms that were in before, but let's describe them now. A charge, for instance, is going to become important in terms of talking about moving electricity. Charge is usually based on the coulomb. The coulomb is a great number of electrons. Now, it may sound like a great number. It's 6 times 10 to the 18th electrons. That's 6 pentillion, 6 pentillion electrons. It's not billion, trillion, quadrillion, but pentillion. And usually that's a sliver of a cup of atoms has that many, atoms or electrons in them. So it really doesn't, it sounds like a lot, but it doesn't take much matter to generate that. One way that's practical to know what a coulomb is how much electricity flows through a light bulb in 1 second. A 100-watt light bulb takes up about 1 coulomb through it. What are more practical ways? Well, a single electron is that 1/6 billionth, or 6 pentillionth, roughly. 1 over that number becomes this number, basically. The charge on 1 electron and 1 proton, and that's the smallest charge. Charge comes in that allotment. You can't get charges smaller because they come as electrons or protons. A static chalk, if you slid across your car and grab your the side and metal of the car, or you walk across the carpet, that's about a billionth or a nanocoulomb. Taking the best, the fur that loses its electrons easiest, and the plastic that grabs electrons the best, the rubber or plastic are great at grabbing electrons, that could be a microcoulomb or a millionth of a coulomb. That's from static charging. Now you can do that over and over again. That's called a Van de Graaff generator, where you just keep taking electrons from something and then depositing them somewhere else, like on the surface of a sphere. And that's why those can get to have so many electrons on them that cause your hair to stand up. But that's the process. Normally just a single rod where you just rub it with some fur, then that's going to give about a millionth of a coulomb. Lightning, of course, is always going to be the key case, and that how much electrons there are in a strike of lightning. 20 seems to be the average amount I see on books. But boy, it can range 10 to 100 coulombs. It depends on how long that lightning is striking. So charge is going to be one symbol, one element of charge, and it's going to give the symbol Q in most formulas, a small q. Then how much energy does that electron have, or how fast will those electrons be coming through the circuit, is going to be measured by potential. Potential is going to give the symbol voltage, or V. And here's some great examples. If there's no potential, then the electron's sitting on a flat surface. And we're going to compare this to a hill. 120 volts, it's going to be a steep hill. Okay, so the electrons are going to get lots of speed as they come through there. That's one way I think about those. A single cell battery, for instance, is 1.5. So either a D cell or a double A, they just don't have as much electrons. D probably have 5 times the electrons, or it can be used 5 times longer. Household outlets usually run at 120, and then if you have a major appliance, actually they run at plus 120 and minus 120, so that if you do put an oven in, you can just take the difference between the plus and the minus 120, and that's where you get 240. Europe, they run them all at 240, pretty much all the plugins. The substations that you see in your neighborhood that the squirrel gets into and it cuts out the power for a while, or something blows there in that neighborhood and causes your neighborhood to go dark, those come out, the electricity is coming out of those at about 50,000, then they get stepped down in your neighborhood to be delivered to your house. And then in terms of some king of voltage, those big power lines that hold those lines, they're at about 500,000 or 500,000 volts. Current. How many electrons are coming? It's the size of the pipe that allows number of electrons through. So current, though, is also the thing that ends up killing you if you get the current across your body. And given in amps, so like I said, the 100-watt bulb is about 1 amp to drive that 100-watt bulb. A 100-watt bulb is pretty big. A lot of that energy is going to heat as well as light in the older ones, but that's why we were looking for more efficient bulbs nowadays. The slight sensation, if you feel a 1 milliamp, 1,000th of an amp, it would feel like, ooh, that's a tingling. You can sense that. And it doesn't take much more before it becomes painful. Like you said, no, I just don't want to touch that again. You may have grabbed an electric fence or bumped into one if you ever worked in the country, or you may have touched something that shorted out. Those are more likely that kind of painful shock where you're like, yeah, that's a little freaky. It's about 7 milliamps, 6, 5, 8, something like that milliamps. But by the time you get to 10 milliamps, if you short out, like for instance, you're grabbing a stove and it shorts or some electric appliance, that will freeze you because your muscles will clench and you won't be able to let go at about 10 milliamps. Okay? What all it takes in terms of death, in most cases, they talk about a range again, but around 15, or selectively, passing 15 milliamps, 1,000th of an amp, through your heart will kill you. It has the potential to kill you. And of course, household circuits run at about 10, and that's the smallest of the circuits that you can get, up to 50, usually for your stove or your fridge or those kinds of things, take a lot of energy. And lightning, of course, that's going to allow, it's a huge pipe, 30 to even 100,000 amps. So if that gives you an idea of how fast current is going, that's one of those. Now, if voltage is how fast things are going through, then resistance or hitting the brakes is what the resistance is. It's usually given the symbol omega, and it's the unit for that is called the ohm. So omega is looks like that watch commercial in terms of those. And so I'll just say that that's going to take away whatever your voltage was providing at the top. Resistance that has a certain ohms value is going to be pulling from that voltage when current flows through there. As a matter of fact, that mathematical expression here is voltage is equal to how much current goes through a resistor of certain resistance. Where you try to push electrons through something, anything that's got resistance, usually we'll give it a symbol, and I'll show you in a second what that is. It's going to be taking away from the voltage. So every time you go through an instrument, you've got 9-volt battery, goes through an instrument, it's come out as 7-volt battery, so that resistance times the current was 2 volts. What also is you run into is the power, how much you pay for in your electric bill, and that's going to be power times time. Power is how much electricity or how much work is going on in a second by time. So if you use lots of current and it's taking short time, that's going to be about the same as using something that's just plugged in and has the little light saying ready and standby like your coffee machine all day. Those two have about the same amount of the lower power use times a longer time will be what you pay for, or a big power use over a short time. That's the current times the voltage. Current is the amount of electrons going by second times the voltage that they're running through there. Power also can be used if you don't know the voltage, because V equals IR, you could replace the voltage here for I times R, and so that becomes 2 I's, or the squared, and times the resistance. You can figure out power in both those two ways. If you take power times time, you'll get the actual amount of energy that you're paying for. And usually they're given symbols like kilowatt hour. So those are a few terms about moving electrons in a circuit.